Is this working? Okay. All right. Well, so on Thursday, we looked at this Olympic data set. Okay. All right. So today, the topic I'm introducing is cross-validation as a method to help you select a model. Okay. So on Thursday, we looked at this Olympic data set, and we were looking at kind of least squares regression, multiple linear regression. We were just fitting different polynomials. We said, let's try fitting a second order, a third order, a fourth order, fifth order, et cetera, et cetera, et cetera. We were trying to see what kind of polynomials would fit, and we plotted this, and we got this little this picture here, so we can see, the linear fit, the quadratic, and second, third, fourth, fifth, sixth order polynomials fit to the data. And the question is, which model fits the best? Now, if your only way to measure which model fits the best was your R squared, or basically the the proportion reduction in sum of squared error, right? So you look at how much sum of squared error is reduced between just fitting a constant value to every value, okay? And you say, okay, well, if I just fit the mean to everything, what's the squared error I would get? And then if I fit this line, this gray line comes a lot closer to predicting this dot right here, and so it's going to have a reduced sum squared error. And if that was our only guide, then what's going to happen is that the most complicated model will always get selected, right? The more terms you add, the more complicated your model becomes, and you can squeeze out a little bit more R squared. You can always squeeze out a tiny bit more R squared. But we know that that is not necessarily the best strategy, and sometimes a simpler, less complex model is better, right? And so the classical approach from 101A would be you'd do like an F ratio test, or you'd at least look at the table of summary, the summary table. You'd look at the kind of the p-values related to each coefficient and things like that. In 101A, do you just look at the table, or do you talk about like the F test that goes into getting those p-values? Yeah. Okay. All right. So and you have the likelihood ratio test and whatnot, right? So those are things that you got. Other tools like the AIC and the BIC. I don't even remember that Akaike information criterion or something, right? You got these different things, and you say, okay. And there's always a little bit of conflict, because it's like the AIC says this one's a little bit better, and the BIC says this one's a little bit better, and you learn a little bit about like one prefers slightly more or something, right? And you have to kind of think about this, and you say, well, what makes sense, right? And it requires a little bit of, I don't know, quote unquote expert knowledge. Hopefully you use a little bit of your familiarity with the subject to do that, okay? So in contrast, I'm going to introduce cross-validation. And again, cross-validation falls under a little bit more machine learning, right? Because when we talk about machine learning, it's all about giving a set of rules to a computer, and a computer is not capable, not yet, of doing original thought, of critical thinking, of thinking expertly about the variables. And so it just says, hey, here are some rules. I'm just going to follow the rules exactly, and this is the decision I'm going to make, okay? And so there is a certain irony, because I think a lot of you want to become, I imagine many of you want to become experts in machine learning. But when you become experts in machine learning, you're effectively trying to teach a computer to do your job, right? So that's like the goal. That's the goal, is to be able to teach the computer so that you don't have to do any more thinking. But I think there's critical thinking. I think will be important for a while. Okay, so anyway, cross-validation is going to remove this kind of skillful, or the flip side is arbitrary thinking, right? you could say I'm being skilled when I'm making these decisions. It just seems kind of arbitrary. And it just kind of, we replace it with this validation strategy. Okay, and that's where we do this cross-validation. And so when we do cross-validation, what we do is we split the data that we have into at least two parts, okay? We'll start off with just two, and there's kind of this idea of like a holdout set and whatnot, but we won't worry about that. But basically, we take the data that we have, and we're going to divide it into training and validation, a training set and a validation set. And the training set is used to fit the model. And what we mean by fit the model is figure out the parameters that go into the model. So for linear regression, fitting the model just means what is the slope and what is the intercept, because that's all you're going to do, right? And if it's a quadratic model, you got to figure out your beta 0, your beta 1, or I guess W0, W1, and W2 terms. You got to figure out the coefficient. Figuring out the coefficients is the idea of fitting the model, okay? And you're only doing this with a subset of the data, okay? So there's going to be values in your validation set that were not used to estimate the coefficients. And after you estimate the coefficients, after you fit the model by using that training data, we take the fitted model, the estimated parameters, to make a prediction on the validation set. Okay, we try to make a prediction on the validation set. I'm sorry, was there a hand raised or a question up there? I don't know. I thought I saw something. Okay. And we're going to use some kind of metric, some way to evaluate, to measure how well does this model work at making predictions. Okay, and mean squared error is a common choice, but we can use different ones. And they have different, emphases, I guess. And we're going to do this for each kind of model that we have. And we can compare the metrics, and we can choose the best performing model. Okay. So a simple one is called leave one out cross-validation. Leave one out cross-validation. So in leave one out cross-validation, the training data is going to be the entire data set minus one observation. We're leaving just one observation out. The one observation out is going to be our validation or our test set. Okay? And when leave one out cross-validation, every data point gets a turn at being the validation or the test data. And you're going to end up with n training sets or n validation sets, okay, and data points. And so to illustrate this, I've got this very, very, very simple toy data set. And we're going to get the leave one out cross-validation error for this very simple data set. Again, the whole point of leave one out cross-validation is to test out different models and compare them. Here, we're not even going to, we can't really test out different models just because the data set is too small to test out different models. So we'll just test out one model, and we'll just get the cross-validation metric for this one data set, okay? All right, and so my data set is going to be X is 1, 2, 3, 4. T, the Y's, or the T, is going to be 1, 3, 2, 4. All right, and what I'm going to do is I'm going to set index 4, that is this fourth observation, to be my validation set. So I'm going to train on the first three observations, 1, 2, 3, 1, 3, 2, and I'm going to test it on the fourth observation, okay? So I'm going to have training X is X minus the index, where the index is the fourth, and the validation X is going to be X, but just the index, okay? So let me just show you. This is the full data set, 1, 2, 3, 4. And if we were to fit a linear regression line to the full data set, this is the line we would get. We would get an intercept of 0.5 and a slope of 0.8. Okay, so this is the data set. But what we're doing with leave one out cross-validation, or even, leave one out cross-validation, we're going to take this fourth observation and we're going to basically hide it. Okay, and so now I just have these 3 points. And so if I cover this up with my literal hand here, if I cover that up, what is the line of best fit for the remaining 3 data points? Okay, this is going to be the line of best fit, right? So this is, for the full data set, it tries to fit that thing, but with just 3 points, this is going to be the line of best fit. All right, and so this line has an intercept of 1 and a slope of 0.5. Okay, and you could test it out and see if you get the same line if you do the process, but you will. Okay, so this is the line of best fit, and so the question is, how well does this line do at predicting the point I left out? The point I left out was at 4, 4. So we're going to put that point back in, and we say, okay, with this fitted line, when x equals 4, the predicted value, I'm going to plug in 1 plus 0.5 times 4, because that's my prediction line. It says, oh, we would predict the value 3. Okay, and how much is the error then between the prediction and the actual value? Well, it's you get a residual of 1, and if you square that error, you're going to get 1 squared, or 1 as well. Okay, and so this would be, at least for this one data point, this is the cross-validation error of 1. Okay, which is significantly more than if we look at this. When we fit the whole data set, your residual here is I think like 0.4 or something. I don't remember what this is, but predict 0.8 times 4 is 3.2. 3.2 plus 0.5, 3.7. Yeah, 0.3. Okay, so the residual here is 0.3, and 0.3 squared is 0.09. Okay, so it's quite a bit smaller here, but of course we don't have the insight of knowing that this data point exists, and so with just these 3 points, this is the line of best fit, and so we have quite a bit more error here. We have a squared residual of 1. Okay, does that kind of make sense? And we do this for every single data point. Every single data point gets to be a validation set. Okay, so as far as calculating this out, I'm going to create a model based on the training data. I'm going to make a prediction using this leave one out model on the validation point. And I use that to make a prediction, and then I'm going to take the difference between the validation point and the prediction and square that difference. So right now this is a 1, and I started off with the total squared error being 0, and I'm going to just add 1. And I'm going to go through and do this for all 4 data points. I'm going to just keep incrementing my total squared error. So right now my total squared error is 1, and we're going to go back. So here's again the full data set. This time we're going to leave out this data point. So if I cover up this data point, what is the fitted line going to look like here? Okay, so if I cover this one up, so if we throw that point away, then this is going to be the best fitting line, right? So that kind of makes sense, right? So if you remove that middle point there, this is going to become the best fitting line. And then we say, all right, how well does the data fit this? Okay, how well does this fitted line predict the point I left out? So here's the point I left out. According to this model, for x equal to 3, we would predict the value 3.28571. Okay, it comes up here. And the actual value is a 2, and so my difference is negative 1.28571, and if you square that, you get 1.653. Okay, and we're going to do this for all 4 data points. All right, and so here's, again, all 4 data points. We throw this one, we hide this one. We hide this one. That's going to be our validation point right here. So we remove that. This is the best fitting line for just the remaining 3 points. We put that back in, and we say how much error is there, and we square that, and that's going to be the cross-validation. So this, because their data set's kind of symmetric, we get 1.6531 again. And then lastly, we're going to remove this one. This will be our validation point. We remove that. For the remaining 3 points, this is the line of best fit. I put this one back in. We say how much error is there. We have an error of 1, and we square that, and we get squared error of 1. Okay, so my 4 errors are 1, 1.653, 1.653, and 1. And so if I add all of those up, I get 5.306. That's going to be my total squared error for the 4 different cross-validation, the sets that I've done. And so if I take that and I divide by 4, then my mean squared error is 1.326. And so this would be the cross-validation, leave one out cross-validation error for this particular data set of 4 data points and fitting a linear regression model. All right. Are there any questions at how we arrived at this number? Okay, let me go ahead and give you your first view quiz answer for today, which is the letter B. B as in bear. B as in bear is your first view quiz answer for today. Okay, now you could go through this process that I went through to calculate your mean cross-validation error, your leave one out cross-validation error, and you would get this number. Thankfully, you don't have to code it all up that way. There is a function in library boot. Okay, in library boot, you can fit a linear model, and there's a function cv.glm, and it will give you your leave one out cross-validation error. So you say, you give it the full data set. So this all data has all 4 data points. And then you fit a linear model. You use a GLM, generalized linear model, so you can technically fit like logistic regression and other models too. Okay, and so we just say predict t based on x. The data is going to come from all of our data, and then perform cross-validation, cv.glm, and you do all data, linear model. By default, cv.glm will do leave one out cross-validation, and this returns a whole bunch of stuff, but the value contained in delta 1, will be your cross-validation error. So you get 1.3265, which is what we found when we did it manually. So if you go through the process, you get the number. And if you go through this, you get the same number. Okay, now, this number all by itself, not useful, okay? It's kind of just like, I don't know, if you have one data set and you calculate the variance, like, okay, I guess that's nice, but it's not very useful until you have something else to compare it against, right? And then it's only like the variance, a lot of these summary statistics only make sense when you talk about, okay, here's one sample and here's the value and here's another sample and here, it's got a different value, and then you can start making comparisons. And similarly, getting this leave one out cross-validation error all by itself isn't very useful until you have something to compare it against, okay? And so this would be the leave one out cross-validation error for a linear model, okay, for a linear model fit to this data set. Now, what we would probably do is we would try a different model. Perhaps we would say, let's fit a quadratic model and see if that does a better job, or let's try fitting a, some other polynomial model. But unfortunately, because I have only 4 data points, if I remove one, then the quadratic model will fit the other 3 data points like perfectly, and it just kind of gets a little bit weird, right? So, but the idea is you're going to get a single cross-validation score for that one model. In this case, it was the linear model. Then you would try a different kind of model, maybe a log model, a polynomial model or something, and you would perform leave one out cross-validation, and you're going to get another number, and you kind of compare that. Okay, so these individual things. So again, this is just kind of the same 4 plots, just showing up again. We train it on here. Here's our squared error. We get 1.6531. Here the other one's 1.6531 and 1, and when you add them up, you get an average of 1.326531. Okay. So we take that, we try a different model, log or something. We're going to fit that one n times to do leave one out cross-validation, take the average, and then we compare cross-validation scores from different potential models. Okay. The individual numbers here, this 1.6531 or 1, and this one, 1 and 1, that does not matter to us. We're only really interested in this average of 1.326531. Okay, we're only interested in this total average after fitting the model n different times. The one individual errors, we don't actually care too much about. All right, is that okay for leave one out cross-validation? And you know, the problem, it's not, I guess it's not too huge of a problem, but a little bit, is when you have a huge data set, you've got to do this process like a bunch of times, right? If you have like 100,000 observations, then you have to do 100,000 kind of cross-validations, because you know, observation 1 is left out, and you fit it on the other 99,999 values, and then you do it, and you have 100,000 different things, and then you have to kind of compare these. So that can take quite a while if you have a very big data set. So the alternative to that would be to do something like k-fold cross-validation. Okay? So rather than just leaving one observation out at a time, you take your entire data set and you divide it into k blocks. Okay? So yeah, this is the issue. With leave one out cross-validation, you're going to have to fit n models for n data points. And if you have a very big data set, this is going to become computationally expensive. You have a lot of models to fit. And because the other thing is, because each model is fit on all but one data point, the resulting models end up looking very, very similar to each other, right? If you look at one model that was fit to 99,999 points, and then another model that was fit to pretty much 99,999 points, you basically have, what, 99,998 points of overlap, and there's really only like one point that's different. And so these two models are going to end up all very similar to each other, and so they're going to end up being highly correlated, and you still run the risk of overfitting your training data, okay? Which is kind of what we're trying to avoid. So for a larger data set, we often try to use k-fold cross-validation. And so we're going to divide the data into k blocks, equally sized, or as much as we can, if it doesn't divide into k evenly. And each block gets to serve as the validation set, and the remaining blocks combine to be the training data. So if we are going to do 4-fold cross-validation, you take your full data set, divide it into 4 chunks, and every time you run, for each iteration, 75% of your data serves as your training data, and the remaining 25% serves as your validation. Okay, so you're going to have 75% as training, 25% as validation, and each block gets to serve as the validation set. Okay, so in general, every observation is part of a validation set exactly one time. Okay, so let's try this out for the Olympic data. My Olympic data, I have 28 observations, and we have 2 variables, the year and the winning race time. Okay. And so what I'm going to do is I'm going to do 4-fold cross-validation. I'm going to take the data and I'm going to divide it into 4 blocks. Now, this is going to be 4 random blocks, and so there is the results of k-fold cross-validation is subject to basically your random seed. So 2 people could do 4-fold cross-validation on the data set and end up with different results, because perhaps for one person, your first block has these 7 points, and then someone else that their first block has 7 different points, and so you're going to get slightly different results from one person to the next when you do k-fold cross-validation. And for each of these kind of splits that we're going to do, I'm going to just fit a whole bunch of different models. Okay, I'm going to fit a linear model, a quadratic model, 3rd order, 4th order, 5th order, and then we'll do an 8th order and a 17th order polynomial just for fun. Okay, so, and what we're going to do is we're going to calculate the total squared error for each of these models, for each validation set. And we're going to find the cross-validation error by averaging the squared error for each model. And we're going to compare, at the end, compare the cross-validation scores to pick which of these models, the linear, quadratic, cubic, 4th, 5th, 8th, or 17th order polynomial, does the best job of predicting our data. Okay, so to kind of split these, I'm going to create 4 different sets: set A, set B, set C, and set D. Okay, and I'm just shuffling. We got 28 observations, and I'm just kind of shuffling them, and I'm putting 7 observations into each set. Okay, and so whenever I fit it, I'm going to take 3 of the sets. I've got 21 observations. I'm going to fit the data to 21 observations, and then we're going to see how well that fitted model works at predicting the remaining 7 points. All right, so this is where we're going to run it, and this is kind of the cross-validation code, if you want to bother reading through it. Basically, I'm going to subset. So in the sets, it's a list of basically 4 vectors here. And we're going to take the index of one of those things. So we're going to say, in the first one, it'll be set A. We'll do these indexes. And we're going to remove those to create our training data. So our training data will be everything except for the observations in the validation index. Okay? All right. And then the validation points will be just those validation indices. Right. And then we create a data frame using the training data. We create a data frame using the validation data. And then what I do is I'm going to fit model 1, which is going to be a linear model between t and x using the training data. And then we're going to make predictions using the predict function, using that model that we just fit, model 1, on the validation data. And then we're going to measure the difference between the actual values in the validation data and the values that we predicted using the predict function. We take that, we square them up, we sum them up, and divide by n. Okay. And then using the same training and validation data, I'll try fitting a polynomial model, okay? A poly 2, a quadratic fit. We're going to make predictions using the quadratic fit. We're going to make predictions on the validation data. We ask for what is the difference between the actual values in the validation data and the predictions I made using this quadratic model. We take that difference, we square them, we sum them up. Okay? And we do this for all of the different models. I've got model 3, model 4, model 5, and model 8, which is an 8th order polynomial, and I think I've got the 17th order polynomial in there as well. But basically all of these things, I'm just fitting a new model using kind of a new polynomial thing, and then we're making predictions using that model. Okay? Every time I fit the model, I'm using only the training data. Okay, only those 21 observations. All right, and that's going to be done for the first iteration, where I used one of those sets to be my validation index. Okay, and then once this completes, we go to the next validation set. Okay, and we repeat the process. And we do this again. We're going to do this a total of 4 times because I've got four sets to be our validation index. Is that okay as far as the code goes? Yes, question.
So for each block, are you computing the mean squared error?
Yes.
Okay.
So I'm computing the mean squared error for model 1, mean squared error for model 2, mean squared error for model 3, and so you can see I've got the cross-validation for the linear fit, cross-validation for the quadratic, cross-validation for the 3rd order, cross-validation for the 4th order, so on and so forth. So I'm keeping track of all of these mean squared errors, and I'm going to get a total of 4 different mean squared errors for each model type. Okay, so I'm going to get at the end, after I run this through all 4 validation sets, there will be 4 values in cross-validations for the linear set, 4 values for cross-validations in quadratic, 4 values cross-validation for 3rd order, and so on and so forth. And then we'll take the average of each of these things. Okay, So just so you can kind of see how this is kind of working, we'll look at validation set C, okay? So technically there's 4 different validation sets. Validation set A, set B, set C, and set D. And just for illustration, I'm just taking one of these validation sets, okay? I'm not gonna go through all 4 validation sets. But just so you can see what's going on, the full data set has 28 points, and just by random chance, these 7 dots in red are the validation points for set C. Okay, so these are the 7 dots in our validation set. So we remove these red dots, and on the remaining 21 points, we fit a linear line, a linear model on the remaining 21. We say, what's the best line that we can fit on these 21 data points? This is the line. And then we say, okay, well, how good or how well did this line predict the 7 points? Okay, so here are 7 red dots. Here's our line. And we say, okay, how well did it predict these 7 points? And we go, oh, it did a pretty good job. Okay, I mean, there's some error here, there's some error here. And so we can say, all right, well, what's the mean squared error for this particular validation set? It turns out to be 0.0319. Okay, and we would have this kind of thing for set A, set B, set C, and set D. There would be 4 of these things calculated on whatever 7 points ended up in that data set. Okay. Let me go ahead and give you your second view quiz answer. Second view quiz answer is A. A as in apple. A as in apple. Okay. So we can see this is how it worked for the linear model. Okay. We'll try this again. This time, okay, again, full data set with our 7 validation points in red. We say, okay, let's remove the validation points. We remove those validation points, and we're going to fit a quadratic model. See, on these 21 points, what is the best fitting quadratic line? This is the best fitting quadratic line on these remaining points. Okay, then we put the 7 points back in. So if I go through it quickly, you can kind of see, right? So these are the 7 points back in. We put this back in, and we say, okay, how much error is there now? And we have, for this particular validation set, our mean squared error is 0.025. Okay. All right, let's do this again. This time we're going to fit a quadratic. I'm sorry, quadratic, cubic. Okay, so we remove these 7 points. What is the best fitting third order polynomial that we get? So now we get a little bit of a S-curve in here. I don't know what we call this thing. Okay, cubic model. We put our 7 points back in, and we say, what is the error on these 7 points? And we get 0.0131. Okay, let's try the fourth order, and we get some error here. And here's the 8th order. Okay, and so you can see the 8th order, it fits this data point pretty well, okay? And there's kind of a little bit of wiggle here. And we get, this is the validation set. So we put the 7 points back in, and we measure how much error is there. Okay. All right, and just for fun, we did the 17th order polynomial, right? So with the 17th order, you have a whole bunch of like wiggle room, right? And so it fits this data point perfectly, that data point perfectly, and like these data points down here, it fits these ones perfectly, right? But what happens when I put the seven red dots back in? Okay, when I put the 7 red dots back in, it does a terrible job at this last point, right? Because its goal was trying to fit this data, the training data as well as it possibly could, and it had no idea that other data points were coming in. Okay, so when it tried to fit the validation data, or not the validation, the training data, it fit this. When we put the validation data, we have this, there's a huge residual between what it's predicting and what it actually is, right? Because with a 17th order polynomial, it just kind of just rockets off in the, as soon as you start extrapolating. So when you look at the mean squared error on this validation set, it ends up being this ridiculously large 1,640, versus everything else is on the order of 0.019 and 0.02 and things like that. Okay, and so this would be kind of a clear indication that something is not quite right for fitting a 17th order polynomial. Okay, so this is what we end up getting. Okay, so if I go through, I can calculate for each of these data sets. We can do what is the cross-validation error for validation set A, validation set B, validation set C, and validation set D. Okay, and so the numbers that we saw were all from validation set C. So we saw the numbers. The linear model was 0.0319, 0.025 for the quadratic, 0.0131, 0.0192, 0.0213. And so we have those 0.0319, 0.025, 0.0131, 0.0192, 0.0271, 0.0213, right? And you can imagine going through the same thing, and we had a cross-validation error of 1,640 for that 17th order polynomial, okay? And we could do the same thing for validation set A, set B, set C, and set D to see what kind of errors do we get. And so each of these things we get something just a little bit different because the 7 points that end up in the validation set are a little bit different. And so the overall cross-validation score, the four-fold cross-validation score, is just the average of these things. Okay, so I take the average of these 4 validation sets, and we get 0.0674. I take the average of these 4 cross-validation scores, and I get 0.0624. Right? So I just want to kind of make sure everybody understands how I'm getting this last column that says cross-validation score. It's the average of kind of the 4 mean squared errors for each of the validation sets. Is that okay? And then so what we do is we look at this cross-validation score and we say, all right, which overall cross-validation score is the lowest? And in this particular generation, when I partitioned my data into 4 folds, the overall was 0.0419 being the lowest. That's the 8th order polynomial. Okay. The second lowest cross-validation score is the 3rd order polynomial, 0.0571, and then the others are a little bit higher, right? Okay, so you kind of pause and if you just said, well, let's just use the lowest cross-validation score, you'd say, okay, let's go with the 8th order polynomial. But then you go, well, sometimes a little bit of thinking is good, and you say, well, what does it even mean for Olympic race times to have an 8th order relationship with the year in which it was held? And I don't know. I don't even know what it means to have a relationship a 3rd order relationship in the year with the year in which it was held. Okay, but we would use this as kind of a guideline. Now, here I just changed my seed. Okay, and again, when you do k-fold cross-validation, and you say, let's partition our data into 4 different sets, which data points end up in which sets is subject to randomness. And so if somebody else did 4-fold cross-validation on the exact same data and the exact same set of models, they might end up getting slightly different scores. And so here I ran through the exact same process, but this time I just randomly changed what my validation sets were. Okay, so I just reshuffled the thing and I said, these 7 are going to be in validation set A, these other 7 are going to be in validation set B, these 7 are going to be in validation set C, so on and so forth. And when I did that, the best performing model, according to the cross-validation score, is the 3rd order polynomial, 0.0464, yields the lowest cross-validation score. And if I did this again, so here's I just shuffled it up again, set seed 10, and I did the same thing. Again, this time, the 3rd order polynomial ends up having the best performing score with 0.0581 here. Okay, so on these slides, I've got a bunch of tables and numbers. And the number that I guess is most important as far as selecting the model is the one in this final column, CV underscore score, and that's the average of the other four columns, which is the cross-validation, the mean squared error for each of the 4 different validation sets that I've created. Okay. Is that okay? What's happening? And so this is a little bit of an illustration of how this process works, but also an illustration that it is subject to randomness. And so you could do, say, 4-fold cross-validation or 5-fold cross-validation, 10-fold cross-validation, whatever you want. But if you have the computational resources to afford it, it might be worth doing a few runs of it with different seeds, different random seeds, to see if you're going to get the same results consistently when you do cross-validation. Okay. Obviously, I mean, you can also do leave one out cross-validation, but that might take a long time if you have a very huge data set. So you might say, okay, let's do 5-fold cross-validation, and let's try it on 5 different random starting seeds, and that might be computationally expensive already as it is. And you can see if the different random starting seeds produce results that all agree with each other, or if they all end up with different results, then perhaps that just means your data is very noisy as well. Okay, so depending on the seed, it's possible to get a cross-validation result where a suboptimal model happens to perform best, right? So when we did this the first time, it said the 8th order polynomial was the best, and that may or may not be the case, right? So it's recommended to run cross-validation more than once. Okay. Now, you could follow the code that I wrote here way back. This mess of a thing where I randomly sampled and shuffled these things around. Fortunately, if you actually want to do something, you can just use something like library boot, okay? And you can do cv.glm, and you can specify an argument k, and that will be how many folds you want. K is equal to the number of folds. Now, by default, k is equal to n, and so if you have n observations and you have n folds, then that's equivalent to leave one out cross-validation. Okay, and then the score that it produces, that you provide is the average scored error, but you can also use some other metrics. So far, we've just been doing kind of mean squared error. So here I run this a couple times, and they say, all right, let's try cross-validation on a linear model. We're going to do cv.glm with 4-fold cross-validation, and I get 0.0643, 0.0659, 0.0576. Okay, slight variation each time I run it, because every time I run it, different values end up in my different folds. Okay, here it is on a quadratic model, 0.062, 0.0469, 0.0648. Here it is on the 3rd order polynomial, 0.049, 0.064, 0.0709, right? So right now these are all kind of all over the place. If you do leave one out cross-validation, you're always going to get the same results, okay? Because when you do leave one out cross-validation, there's no variation as far as what's in the validation set. Every observation is in the validation set. It is the validation set exactly one time. Whereas over here, your validation sets are subject to randomness. Okay, so in summary, this is what we have, right? So cross-validation, and I've taken a lot of this just straight from Wikipedia if you look up the entry on cross-validation. Cross-validation is a method to see how a particular model will generalize to new data. The goal of cross-validation is to test the model's ability to predict new data, even though it wasn't part of estimating it, in order to flag problems like overfitting, which is what we saw in this thing, right? We fit this data, we overfit this data, so we were able to predict these things very well. But when it comes to predicting new points, we see, oh, it does a really bad job, okay? And multiple rounds of cross-validation are performed using different partitions. The validation results are combined to give an estimate of the model's overall predictive performance. And this, again, it removes a lot of the critical thinking as far as how do we go about selecting a model. A lot of times you just say, hey, let's try this one out, let's try this one out, let's try this one out. Let's run it several times, and we'll just do cross-validation to see which one does performs the best. It's there's pros and cons to it, and the pros are you don't have to think very hard, but the results are pretty good as far as detecting things like overfitting, just because you're kind of doing like a mini test run on using the data that you have available. Okay, the cons are almost the same reasons, right? You don't have to think. You don't have to think very hard. That's a pro and a con. Okay, and it's also subject to randomness, as we saw, and it's also highly dependent on the data that you have available in the first place. So, if the data you have available looks like the data you're going to see in the future, that's great. Okay, but if what's going to happen in the future is very different from what's happened in the past, then your model is always going to be trained on the past data, and that could run into problems, right? And so, okay, I'm a minute over, but one thing we've seen a lot of, machine learning algorithms. If you an example is on your camera. A lot of your cameras on your smartphones have kind of these algorithmic tweaks to make your pictures beautiful, right? And it's all based on the image data that has been fed in. And if the image data that has been fed in is not an accurate reflection of the kind of pictures you're going to take, it's not going to do a very good job. Okay, but anyway, let me give you your last view quiz answer. Last view quiz answer for today is the letter B. B as in bear. B as in bear is your third view quiz answer. Okay, that is it for today. Have a good rest of your day. We will see you on Wednesday.